Welcome back. As I said at the end of the last lecture, we will now study the effect of gravitational waves when they pass through various test particles. And we recall that when we studied the equation that describes the behavior of infinitesimally close or nearby geodesics, that led to the geodesic deviation equation. So this is the equation that we need to study in order to do this. Let's write this down. The behavior of freely falling nearby test particles is described by the geodesic deviation equation. Let's write this down. We introduce this notation capital D over capital D lambda squared. Lambda is our affine parameter of the geodesic. Here we have the Riemann curvature tensor contracted with tangent vectors Tj and Ts, which are the tangent vectors of the geodesics, and here we have our vector Ni that connects the nearby particles. And our Riemann tensor here R is the Riemann tensor of the gravitational wave. What I mean by this is in the previous lecture we derived an explicit solution for this quantity h over bar, which then is related to an explicit expression for the quantity h, which is the metric perturbation. And then once we know the metric perturbation, we can compute the metric tensor, which is eta plus h. Once we have the metric tensor, we can compute the Christoffel symbol components and then the Riemann tensor. This is what I mean by this one sentence here, that R is here the Riemann tensor of the gravitational wave. Next, we have our tangent vectors. The tangent vector Ti corresponds to the test particles for velocity. And we can choose this to be simply the vector with components 1, 0, 0, 0. I should really write this as a column vector instead of a row. But as you know, the index position determines the type, and this is just an explicit construction or an explicit mention of its components. It would be more elegant. Let's write it the correct way, so not to confuse anybody anymore. Let's write it like this. And why can we neglect deviations from this very simple form? Simply because R is already of the order h, which is small, which means any deviation of t from 1, 0, 0, 0 the simplest tangent vector we can think about of a particle at rest, that would lead to higher order contributions, which we can hence neglect. So hence, if we now look at this term in the bracket, Rijsa TJTS, given that the three spatial components are 0 and the time component is 1, what we have here is Ri0, 0, A, T, 0, T, 0. Because T0 is 1, we get just this, which means our geodesic deviation equation contains now only those components, and here we have the Ni. We had already an explicit expression for this Riemann tensor a few lectures ago when we did the weak field approximations. And now I'm just stating the result. The non-vanishing Riemann tensor components in lowest order in H are if we look at this now, we will only need very few components of the Riemann tensor. One of them that we need is this one, R1001, which is the same as minus R2002. Both these components are minus a half A plus omega squared cosine omega z minus t. And the other components that we need are 1002, which is the same as 2001, and these are minus 1/2 A cross omega squared cosine omega z minus t. You recall that our perturbation h, after we chose the most convenient coordinates that we could come up with, only contained 2 degrees of freedom, the A plus degree and the A cross degree. And the other 8 components of h were either the other 8 independent components were either 0 or related to A plus and A cross. So in particular, h was chosen in what we called the transverse traceless gauge, so that the gravitational wave's action is transverse to its propagation. Propagation is along the z direction, and it was traceless. In the diagonal, we had those components A plus and then minus A plus, and A cross were the off-diagonal components. Finally, we can choose n. We can choose the vector ni connecting nearby particles to be of the form zero, n1, n2, 0. Why is this? Well, we have coordinates t, x, y, z. We have our gravitational wave that propagates along the z direction, and we chosen a gauge where the action of the gravitational wave is in the transverse plane. If the propagation is along the z direction, then xy is the transverse plane. Maybe I should draw a little picture of this. Here we have our z-axis. Then here we have a plane. This is our xy plane. Normally we draw a wave a bit like a wavy thing like this. It's quite difficult to visualize a gravitational wave, to be honest. The idea is that we have our xy plane, propagation along the z direction, our gravitational wave coming here, and then in green I will have some test particles. Our green dots here are the test particles. And what will happen is the gravitational wave will propagate through this plane, and this will have an action on those test particles. They could, for instance, move a little bit away from the center when the gravitational wave goes through. And then they go back to their original state. Although the way we've modeled this, we have a continuous gravitational wave, so there should be some form of continuous action. Let's write down the equation that govern the behavior of these nearby test particles, and this is precisely what this geodesic deviation equation does. This means we have a wave propagating along the z direction. We have test particles in the xy plane, initially at rest. You can't really decouple it because, as I said, we are modeling a continuous gravitational wave, but in the absence of the wave, these particles would be at rest. And for this setup, the geodesic deviation equation becomes the following. All we have to do, we have an explicit expression for the n, which only has components in the xy direction, as every vector that connects any two of these points will be a vector of this form. We have our Riemann tensor linearized. You can now think about as A, your small quantity, because H was written as A times the cosine bit. These are the amplitudes, which are assumed to be small. We already settled on this tangent vector for a particle initially at rest, and any deviation from this is a higher order contribution anyway, which means all we have to do now is write down the full geodesic deviation equations here. Or becomes, we can argue about this. You can verify that the components n0 is 0. The component n0 will obviously have a 0 on the left. It will also have a 0 on the right, likewise n3, which means the equation for the t component and the equation for the z component both vanish identically, which means we are left with two equations. Here is d lambda squared. The first one is minus a half a plus n1 plus a cross n2. Here we have omega squared cosine omega z minus t. The second equation, d squared n2 d lambda squared minus 1/2 a cross n1 minus a plus n2 omega squared cosine omega z minus t. And all we now have to do is solve these equations. Because the right-hand sides here are, so n1 and n2 are our unknown quantities, we have two second-order differential equations for those n's. The easy one to solve, or if we look at this, the one that is quite easy to solve, if you set a cross to 0, then the equations decouple. When a crosses 0, you have here an equation for n1, second derivative of n1 is this guy, and the second derivative of n2 is that guy. Which means if a crosses 0, then the a plus wave is fairly easy to understand. If a plus is 0, the equations are then coupled, because n1 is determined by n2 and n2 is determined by n1. You can, however, differentiate this twice again and you would end up with one simple equation, because you can eliminate this. You can fairly easily convince yourself that solutions to these equations describe some form of harmonic oscillations. Solutions to these equations describe harmonic oscillations. And as I indicated here, what one tries to do is you are trying to think about a ring of test particles. Let us consider a ring of test particles. and a gravitational wave passing through this ring. What happens is, I'll draw a nice picture in a minute, the ring deforms to an ellipse but the enclosed area remains constant. Which means we just have a distortion here. Recall that A plus and A cross were the two physical degrees of freedom. We are dealing here with linear waves, which means if we first study the A plus wave and then the A cross wave, then we know that any other wave is a linear combination or superposition of those two waves. We'll do the easy one first. For the A plus wave, which means we set A cross to be 0, we have the following picture. This is sort of the picture you should try to have in mind. Let's see if I can draw this nicely. And I think I used dark green for my point part, for my little test particle, so I'll try to do this again. Here we have a circle. An ellipse, a circle, and then another ellipse. Unfortunately, it doesn't want to recognize my ellipses. It's the best I can do. This would be the time t equals 0. You see here that we have a frequency. It would be nice if there was a factor of 2 pi in there, but it isn't. So if you just imagine that we split the waves into a total period of 2 pi, then here we would be at pi over 2. Here half the wave is through, and here 3/4 of the waves is through, which is 3 pi over 2. The idea is that you have your ring of test particles aligned on the circle, and this is the experimental setup you would try to achieve. Have a number of test particles and see if there's a strong astrophysical event that you believe will contain strong gravitational waves. Then these waves, as they pass through your setup, should distort the nearby test particles. This is quite difficult to do from an experimental point of view, but has been achieved now. For the other wave, for the A cross wave, one finds pretty much the same picture, just rotated a little bit. Let me try this one again. That came out right bad. God. Okay, I'll pause this video for a minute and then I'll draw a nice ellipse and then I'll turn it back on. I just learned I'm very bad at drawing an ellipse like that. There it is, the best I can produce, handwritten. And again, we have here the time t equals 0, t equals pi over 2, t equals pi, and t equals 3 pi over 2. And what I want you to look at here is the relative orientation of the ellipses in the two cases. And you see that the solution is a rotation. They're both related by a simple rotation. And what we are seeing here is that the A plus wave and the A cross wave, they correspond to the two different polarizations of the gravitational wave This is similar to electromagnetism, where you also have an electromagnetic wave and it has two polarizations. The difference is that here they are related by a pi over 4 or 45-degree rotation. In electromagnetism, they're related by a 90-degree rotation, and that has to do with the spin of the underlying field. In electromagnetism, you have a spin 1 field that mediates the force, while in general relativity, one is working with a massless spin 2 particle. If that doesn't make sense to you right now, that's fine, but some of you will have had a course where this was covered to some extent. And that is the end of our discussion of our gravitational waves, which means now we can study the Schwarzschild solution, which is a static and spherically symmetric solution of the field equation, and the object that eventually, not the object, but this solution then gave rise to the notion of black holes and black hole physics. And is a very nice solution, very easily constructed. And again, after a little bit of work, we can find a few very nice results, which is what we'll start in the next lecture. Thank you very much.